Okay, so we proceed to the next topic. This is the projectile. So projectile, for example, we have this case. So an object is thrown from this elevation and it may land on a higher elevation. If the second point or the final point is higher compared to your initial point, we are to use a sign convention for y, that is a positive y. If it is lower, we assume that to be supposedly negative. So for example, this is the initial direction of the projectile. We are just to assume a small strip of its trajectory. So let's say this is the initial velocity. Since it is inclined with respect to the horizontal with an angle, let's say theta, it will have a horizontal component bx and a vertical component b sub y. So to compute for those two, we have b sub y is basically equal to the initial velocity sine of theta, and b sub x is equal to the initial velocity cosine of theta. Okay, those are the two components. Now, how can we compute for y, for example, for this case? So let us recall one of our basic equation. That is, we have s is equal to b1 initial velocity times time plus 1/2 acceleration due to gravity, the time squared. Okay, take note. Okay, when it comes to projectile, if you are dealing with the horizontal distances, always use the horizontal component of the velocity. If we are dealing with vertical distances or heights, use the vertical component of the velocity. So for example, I'll be using s, okay, so that is basically displacement, s, or distance. So what if that s corresponds to y? What component of the velocity are we going to use? Since y is a vertical distance, we have to use the vertical component of the velocity. What is the vertical component of the velocity? We have, that is b sub o sine of theta multiplied by time plus 1/2. Okay, we have here, since the initial direction of the projectile is upward, we assume the sign convention of the acceleration due to gravity to be negative, the time squared. This is our equation considering vertical component. How about horizontal component? So, okay, take note that we have b sub x is constant. It will not change, okay, at any point of the trajectory of a projectile. The horizontal component is constant. Unlike the vertical component, it is varying. So we have, okay, that is b sub y. The vertical component is a variable. It is changing. Alright? While the horizontal component is constant. If it is constant, basically, the horizontal component b sub x is basically equal to the distance over time. What is our distance? This is a horizontal component of the velocity. So therefore, we are considering horizontal distance over time. What is the equivalent of this one? We have b sub o cosine of theta equal to x over time. So the equivalent of the time will be x divided by the initial velocity cosine of theta. So we substitute the equivalent of the time to our initial equation. Okay, we have this is y is equal to initial velocity sine of theta. What is the equivalent of time? The time is the x distance. So sometimes the x distance, the proper term for this one is this is the range. That is the range divided by the initial velocity cosine of theta. And then we have, since this is negative, minus 1/2 of g. What is the equivalent of time to be squared? That is x divided by initial velocity cosine of theta. This is quantity squared. Then we simplify. So we may cancel b sub o. We have now the equivalent of y. That is, what is sine over cosine? That is, we have x. Sine over cosine is tangent of theta minus the acceleration due to gravity. We have x squared. This is divided by twice of the initial velocity squared, cosine squared of theta. So this is our equation for the vertical displacement. Okay, for the cases that the projectile will fall on a higher elevation, that will be positive y. If it is on lower elevation, that will be negative y. So let's have an example. Okay, so let's have an example for this case of projectile. So a projectile is fired upward to the right at an initial slope of 4 vertical, 3 horizontal, and hits the ground at a point 2 meters higher than the origin. So the maximum height is attained 8 meters away from the origin. So what is the initial velocity in meters per second? First, we are to determine the angle. Tangent of theta is equal to opposite. We have 4 divided by 3. So our angle will be equal to 53.30 degrees. That is for a 345 triangle. So the question is, can we directly use that equation? The y is equal to x tangent of theta minus the gx squared divided by twice initial velocity squared cosine squared of theta. So basically we cannot use this directly since we don't have the range. The range is not given. We have only the value of y, but we don't have the value of the range. So all we have to do for that case is we use the other given. We have an 8 meter. So 8 meters, that is the distance of the maximum height of the projectile. By the way, how to compute for the maximum height? So for maximum height, we are using the other equation from our previous discussion. B sub 2 is equal to B sub 1 squared minus 2g h, since negative g, since the initial direction is upward. Okay, at maximum height, the final velocity or the vertical component of the velocity is 0. That makes the equivalent of h. Okay, if it is b sub t equal to 0, that will be our maximum height. That is equal to b1 squared divided by the 2g. Or this is the same as initial velocity sine of theta quantity squared divided by 2g. So why is it we're using the vertical component? Take note, h is a vertical distance. So we use the vertical component of the velocity. Okay? So we have h max and 8. What is the coordinate of this point? The coordinate, let's say 8 meters is x sub 1. And this is h max, the maximum height. So all we have to do is rename these values, the y and x. So take note, the coordinate of the final point is xy. Still, this is the same as x distance, the same as y distance. It's just, it is the maximum height. So instead of using y, we are to use the h max, or the maximum height. Instead of using x, we have to use the x sub 1. That is the given, 8 meters. So we have to use the coordinate x sub 1, h max, as substitute for the value of x, that is the total range, and h max for the y. Still, this is a coordinate. Take note, if you are analyzing projectile, analyze every point as a coordinate so that you can use your equation. So we now substitute. Okay, what is the equivalent of h maximum? That is equal to initial velocity sine of theta. What is our theta? That is the sine of 53.13 degrees. This is quantity squared. This is divided by twice of 9.81. Okay? So we are using this equation. The y is equal to x tangent of theta minus gx squared divided by twice initial velocity squared cosine squared of theta. So again, what is our substitute for y? That is h max. Equivalent of h max, this is b sub o sine of, we have that angle, 53.13 degrees. This is quantity squared divided by twice of 9.81 is equal to, what is equivalent of x h max? This is our x sub 1, we have 8 meters. the tangent of 53.13 degrees minus 9.81 multiplied by x of 1. We're using x of 1, that is 8 meters squared, divided by twice initial velocity squared. This is the cosine squared of, or cosine of 53.13 degrees squared. So as you can see in this equation, we have a single unknown, that is the initial velocity. So waiting for that value. Mukhang hindi kaya ni Canon yung problem by Shipso. Pag hindi kaya, parang by trial and error. Or you can simplify, but it will be a 4th degree equation. Alright, that is equal to 12 point. It's equal to, this is 12. It's equal to 12.7, 87 meters per second. Let's check on our choices. 12.787, we have letter A, that is 12.79. So our next case, if we have this one, if the projectile will fall on the same elevation as the initial point. So we have this as your range. Let's say this is x. In some references, they are using x. In some, we have r. But this is the same as the range. So from our previous equation, we have the y is equal to x, the tangent of theta, so this is theta, minus gx squared divided by twice the initial velocity squared of cosine squared theta. So what will be the values or the terms that are to be eliminated if the projectile will fall on the same elevation? We'll be having a value of the value of y equal to 0, since we don't have a vertical displacement. So if that is 0, then we simplify. This is x, the tangent of theta is equal to gx squared. This is divided by twice initial velocity squared cosine squared of theta. We can cancel one of the x, then equate to 1x here, the remaining term of x on this side. We have that as we have x is equal to, we have 2 initial velocity squared cosine squared of theta multiplied by tangent of theta, that is divided by the acceleration due to gravity. Then we simplify. You have the value of x na equal to twice initial velocity squared. This is cosine squared theta. Equivalent of tangent is sine of theta divided by cosine of theta divided by the acceleration due to gravity. Okay, we can cancel one of the cosine. So we have the value of x is now equal to initial velocity squared to sine theta, the remaining cosine theta divided by acceleration due to gravity. What's the equivalent of 2 sine theta cosine theta using Pythagorean identities? We have the sine of 2 theta is the same as 2 sine theta cosine of theta. So we'll be having the final formula. In some references, they're using x, some are using r, equal to the initial velocity squared sine of 2 theta divided by the acceleration due to gravity. So this is the formula for the range for the case that the projectile will fall on the same elevation as the initial point. So let's have an example. Okay, let's have this example. So a bullet is fired from the ground at an initial velocity of 350 meters per second and an angle of 50 degrees with the horizontal. Find its range on the same horizontal plane through the point it was fired. So we are just looking for the range equal to the initial velocity squared. This is sine of 2 theta divided by the acceleration due to gravity. We're having the value of x so equal to initial velocity is 350 squared. This is the sine of twice up 50 degrees. This is divided by acceleration due to gravity 9.81. So we have the range. We have 350 squared sine of 100. That is divided by 9.81. So we're having a value of 12,297.548 meters. That will be the horizontal displacement or the range. 12,297, nearest value we have letter A, 12,298. So let's have this case. As you can see, we have a snooping ground. So a projectile is launched at 10 meters per second from a sloping surface. The value of alpha, that is the angle between the sloping ground and the initial direction of the projectile, we have 80 degrees. Determine the total time of flight. For this case, we don't have a new formula. All we have to do is express everything into our two components, the horizontal component and the vertical component. So, when it comes to displacements, what are the components of this incline range? We have x. If this is 30 degrees, this is the same as 30 degrees. What is the equivalent of x in terms of the range? That is the same as the range cosine of 30 degrees. Okay, so the projectile will fall at a lower elevation. We'll be having the value of y. That is r sine up at 30 degrees. Okay, we have the value of y. That is the vertical displacement is r sine up 30 degrees. Again, if a projectile will fall at a lower elevation, our sign convention should be negative for the value of y. So how do we compute for the time of flight? If we have now the displacement. So for the horizontal component, let's say this is for the x component, we have the velocity along x is equal to x over time. We're looking for the time. What is our b sub x? By the way, so that is the same as b sub o. B sub x is cosine of theta equal to x divided by the time. Okay, so what is the value of our theta? What is the value of theta? So take note that if we are computing for the component of the projectile, always consider the angle with respect to the horizontal. If this is 30 degrees, this will be our theta supposedly. This angle with respect to horizontal, that is the value of theta. And that value of theta is the same as the 80 degrees minus 30 degrees. Our theta should be equal to 50 degrees. So that should be our reference angle with respect to horizontal, always. So we have Okay, we have the initial velocity, that is 10. Okay, we have 10 cosine of 50 degrees is not equal to x. What is equivalent of x? We have r cosine of 30 degrees divided by the time. This is our equation using the horizontal component or the x component. How about the y component? Okay, for the y component, we are using this one, the s equal to initial velocity time plus 1/2 80 squared. So if we are using y, we'll be using the base of O, sine of theta times time, minus 1/2 g times the time squared. So why is it minus again? Since the g will be negative, since the initial direction is upward. What is our y? Our y is equal to, it will fall at a lower elevation. We are using negative sign, r sine of 30 degrees equal to initial velocity, vertical component, that is 10 sine of 50 degrees, the time, minus, we have 1/2 of 9.81, the time squared. This is our equation using the vertical component. So, how do we solve for time? How do we solve for the time? So maybe we can express the value of r in terms of time from the first equation. So if the value of r is not equal to, we have 10 cosine of 50 degrees times the time. This is divided by cosine of 30 degrees. Then we substitute this value of r to our second equation. So that is, we have negative, what is the value of r? 10 cosine of 50 degrees times the time. This is divided by cosine of 30 degrees. Or that is the equivalent of r multiplied by sine of 30 degrees is equal to 10 sine of 50 degrees times the time. Then minus, this is 1/2 of 9.81, the time squared. So as you can see, in this equation, we have a single unknown, that is the time. So computing for that value, so we have a time of 2.32 or yes, 2.318 seconds. So that will be the time of flight. And our choices, we have letter C, nearest value 2.32 to the value 2.318. As you can see, all you have to do is manipulate the existing equations before, or our initial equations. All you have to do is manipulate, substitute, okay? Substitute, then formulate your own equation to solve this type of problem. Okay, so let's have this topic. We have work. So work is basically equal to the force times the displacement. If the force and the displacement have the same direction, that is a positive work. So if they are opposite in direction, we have a negative work. So for this example, a force of 200-pound force acts on a block at an angle of 28 degrees with respect to horizontal. The block is pushed 2 feet horizontally. What is the work done by this force? So let us compute for the work. As you can see, the units of the choices, we have joules. So English units, we need to convert into metric. So we have, take note that the motion is horizontal. Therefore, we are only considering the horizontal component of the force. So we have, that is, We have our force is 200 pound force, cosine of 28 degrees. Then we need to convert this to newtons. So this is multiplied by, we have 1 kilogram is 2.2 pound force. Then multiplied by 9.81 newtons is 1 kilogram. That is our force. Then we convert the displacement 2 feet to a meter. So this is multiplied by, we have 2 feet. This is 2 feet multiplied by, we have 1 meter is to 3.28 feet. Okay, so let us compute for this value. The remaining unit will be the same as Newton meter or the joule. So this is the same as 200 cosine of 28 divided by 2.2 times 9.81 multiplied by 2 divided by 3.28. So we have that value as 400. This is 480.139. 480.139 Newton meter or the joules. So on our choices, 480.139, we have letter C, the nearest value, 480 joules. Okay, so problem number 14, this is work done by a spring. So the work done by a spring is equal to the integral of the spring constant times x dx. So if we are to integrate this term from 0 to x, for example, we have the work is equal to, this is k, what is the integral of x dx? That is x squared over 2. Or simply, we have the work done by a spring is 1/2 k x squared. So wherein our k is the, this is the spring constant. And for this example, so it takes a force of 130 newtons to stretch a spring by 30 centimeters. Find the work done in stretching the spring by 20 centimeters beyond its natural length. So the equivalent of the spring constant is basically equal to, this is the force divided by the deformation. For this example, the deformation is equal to 50 centimeters. So if you are to compute for the spring constant, okay, we have the spring constant is equal to a force of 130 newtons. This is divided by 50 cm or 0.5 meter. So you have a spring constant of, this is the same as 130 times 2, so it's divided by 0.5. It is equal to 260 newton per meter. So for the work done, we have a value of x is equal to 20 centimeters or 0.20 meter. So we have the work is equal to 1/2 the spring constant x squared. Okay, we have the work is equal to 1/2. What is our spring constant? That is equal to 260 newton per meter. And we have the value of x is 0.20 meter. And this is quantity squared. So let us compute for the work done by the spring. This is equal to 0.5 by 260 divided by 0.2 squared. So we have a work of 5.2. If we are to do unit analysis, this is named as Newton meter, or that work is equal to 5.2. Newton meter is the same as the joules. So 5.2 joules, we have letter D. We proceed to friction. If we are considering forces that already affecting the motion of a body, this is already kinetics. For example, we have this body or a block having its own weight is acted by this force P, or it is pushed by this force P at a distance, let's say over a distance S. Okay, so how do we analyze this body? So we have the force P, we have the weight. So what are the forces to be considered? If this is in contact with the surface, we have it is always opposed by the let's say frictional force. Frictional force is basically equal to the mu, that is the coefficient of, if it is in motion, this is the coefficient of kinetic friction multiplied by the normal force. What is the normal force? That is any force that is perpendicular to the contact surface. So this is the normal force. As long as this force is perpendicular to the contact surface, that is the normal force. So other than that, if we have, for example, initial velocity 0, then the velocity suddenly increases, or that is greater than 0. Therefore, we have an acceleration. If a body is accelerating, it is acted by an opposite force or an opposing force, which is in other reference, inertial force. In other reference, we have the reverse effective force, or the same as the mass times the acceleration. This is by the second law of motion by Newton. So if we are now to do summation of forces horizontal, and the summation of forces horizontal equal to 0, so we have the applied force P, that is minus the frictional force, it always opposes the motion. The same with the inertial force, let's say the reverse effective force equal to 0. This is the applied force P minus, or is equivalent of frictional force, coefficient of kinetic friction times the normal force, minus reverse effective force from second law of motion by Newton, that is the mass times acceleration equal to 0. But not all cases, these three forces are present or available. There are cases that one of them is missing. It depends on the problem. So let's have one example. Okay, so let's have an example. A 100 kilogram of ice is kicked so that it will have an initial velocity of 10 meters per second. If the coefficient of friction between the floor, which is horizontal, and the block is 0.1, we assume this to be coefficient of kinetic friction. Find the total distance that the block will travel before coming back to rest. Coming back to rest, which means the final velocity should be equal to 0. So let us analyze the block while moving. So after kicking the ice, it moves on its own. So therefore, we don't have a constant force applied to the block of ice. So what are the forces that are we going to consider? Since we have a change in velocity, therefore we have an acceleration. So if we have an acceleration, therefore we have a reverse effective force or an inertial force. If we have a coefficient of friction given on the problem, therefore we are considering frictional. We are also considering frictional force. Okay? So by summation of forces, horizontal equal to 0, to the right forces to be positive. We don't have the force P or the applied force on the block for this case. That is negative reverse effective force minus the frictional force is equal to 0. What is the equivalent of REF? That is the mass times acceleration. Frictional force, coefficient of kinetic friction multiplied by the normal force. So what is our normal force? For this case, basically if we are to do summation of forces vertical, the normal force is simply equal to the weight of the block of ice. So therefore, we have the normal force is equal to the weight that is the mass times acceleration due to gravity. We have a normal force equal to, what is the weight of the block of ice? We have 100 kilograms times 9.81. So a normal force equal to 981 newtons. Okay, so we are now to substitute on this equation to determine the acceleration of the block. So, computing for that value, we have negative, that is negative 100 times the acceleration minus the coefficient of kinetic friction 0.1. Normal force is 981 newtons equal to 0. So let's compute for the acceleration. Okay, so we have is equal to negative 0.981 meter per second squared. So why is it negative? Why is it negative? As you can see, this is slowing down from 10 meters to 0. That is deceleration. That's why it is negative. So if you have no acceleration, we have an initial velocity equal to 10 meters per second. How do we compute for the distance? What is the most suitable equation that can be used to solve this problem? Okay, we can use the first one from our previous discussion. That is the final velocity squared equal to the initial velocity squared plus twice acceleration times the distance. What is our final velocity? That is 0. What is our initial velocity? We have 10. That is 10 squared plus twice. Okay, this is deceleration, slowing down, negative 0.981 times the distance. So, computing for the distance, this is now equal to, it's the same as 100 divided by twice of 0.981. So we have a distance of 50.968 meters. Before coming back to rest. On our choices, we have the closest value to 50.968 is 51 meters. Letter B. Okay, for our next example, this is an inclined plane. So a block initially at rest slides down an inclined plane at angle 30 degrees with the horizontal. The block is placed at a vertical distance 60 meters above the bottom of the inclined plane. The coefficient of kinetic friction between the block and the plane is 0.25. So you have mu kinetics equal to 0.25. So which of the following most nearly gives the acceleration of the block? So we have this block. So all we have to do is first do our free body diagram, starting with what are the forces acting on this block. So obviously we are to start with its own weight. So the weight of the block. So since it is inclined, the weight will be having two components. One component that is parallel to the inclined plane, it is parallel to the inclined plane, and the other is perpendicular to the inclined plane. If this is 30 degrees, this angle is the same as 30 degrees. You can prove that geometrically. Okay? So therefore, this is the weight sine of 30 degrees. That is the parallel component. Perpendicular component is W cosine of 30 degrees. If we have a coefficient of kinetic friction, therefore, if the block is to move downward or accelerate downward, it is opposed by frictional force. As I said, this is our frictional force. Then, if it is to accelerate, also, it is opposed by the inertial force or the reverse effective force. So we have our normal force this time. What will be the equivalent of the normal force? Take note that it should be perpendicular to the surface. So our normal force for this case is the same. If we don't have any other force or external force, the normal force is equal to the weight cosine of 30 degrees, equal to the perpendicular component of the weight. So if we are to do summation of forces equal to 0, let's say upward incline to the right to be to the left. Upward forces to the left will be positive. What are those forces? We have the frictional force, we have the reverse effective force, and the only downward force parallel to the surface is the W sine of 30 degrees equal to 0. As you can see, the weight is not given. What is the equivalent of frictional force? Mu kinetic normal force. What is the equivalent of REF? The mass times the acceleration minus the weight times sine of 30 degrees equal to 0. So we have, what is the equivalent of mass? Weight is equal to mass times acceleration due to gravity. Therefore, mass is equal to weight divided by the acceleration due to gravity. So what is our mu? The mu is equal to 0.25. Equivalent of normal force is the weight cosine of 30 degrees plus, what is the equivalent of the mass? Mass is weight divided by g divided by 9.81 multiplied by the acceleration minus the weight times sine of 30 degrees equal to 0. As you can see, all terms have all terms has this the element of weight. So we may divide all terms by the weight to eliminate the weight. Okay, so we have the simplified equation, 0.25 of cosine of 30 degrees plus the acceleration divided by 9.81 minus sine of 30 degrees equal to 0. Therefore, we can now solve for the acceleration. So the acceleration is the same as 0.25 cosine 30 minus sine of 30 transpose, it will be positive times 9.81. That is, we'll be having an acceleration of 2.781 meters per second squared. So 2.781 meters per second squared, we have letter D, 2.78. I will proceed to the law of conservation of momentum. Basically, we have momentum is equal to the mass times velocity. That is the equivalent of momentum. So we have two main cases. This is the study of colliding objects. So for example, we have mass 1 and mass 2. They are about to collide. So for example, they collide after the collision. They separated on, let's say, mass 2 on the right, mass 1 on the left. So we have conservation of momentum. That is the mass or the momentum before collision. What is our momentum before collision? That is mass 1 B1, mass 1 B1 plus mass 2 B2 is equal to the summation of the momentum after collision. That is mass 1 B1 prime, since B1 is no longer equal to B1 prime after collision. The velocity before and after collision are not equal. Plus, we have mass 2 B2 prime. This is our first case. If after collision, the bodies separated. So the value of the coefficient of restitution for this case is greater than 0, possible that less than or equal to 1. This is the value of the coefficient of restitution. For this case number 2, again, we have two objects that are about to collide. After collision, they stick together, then they move as one. So our equation for that is, what is our momentum before collision? That is mass 1 B1 plus mass 2 B2 is equal to, if they stick together and move as one, combined masses, M1 plus M2, then a common velocity. The value of the coefficient of restitution for this case is, we have 0. So the equation of the coefficient of restitution, that is E, is equal to, we have B2 prime minus B1 prime divided by B1 minus B2. Okay? So let's have an example. Okay, so our next example. So the bus B has a weight of 15,000 pounds and is traveling to the right at 5 feet per second. I said it as mass 2 B2, 15,000 pounds and 5 feet per second. Meanwhile, a 300-pound car A is traveling at 4 feet per second to the left. If the vehicles crash head-on and become entangled, determine their common velocity just after collision. Entangled, which means we have to combine the masses, which means after collision, they stick together and they move as one. Which means that is our case number 2. That is the mass 1 B1 plus mass 2 B2 combined masses. This is mass 1 plus mass number 2, a common velocity since they are entangled. What is our mass 1? We have that is equal to 3,000. 3,000. So we may use our sign convention. According to the problem, the bus B has a weight of 15,000 pounds and traveling to the right. So let's say B sub 2 is to the right. We assume that to be positive 5 feet per second. While for car A is traveling at 4 feet per second to the left. That is our B sub 1 to the left. We assume this to be negative 4 feet per second. Since it is, that will be our sign convention. To the left, negative. To the right, positive. So this is 3,000 to the left, negative 4. Plus our mass 2, we have 15,000. This is multiplied by its velocity, 5 feet per second to the right. Then our masses, we have 3,000 plus 15,000 multiplied by their common velocity after collision. So what will be their common velocity after collision? So we have 15,000 multiplied by 5. Minus 4 times 3,000. This is divided by 18,000. Okay, so we'll be having a velocity of 3.5 feet per second. If it is positive, which means its direction is towards the right. Towards the right direction. And as you can see, we have 15,000 pounds traveling at 5 feet per second to the right. Take note that mass 2 B2 has a greater value of momentum compared to car A. In this case, this is the momentum for bouncing object. So a ball is dropped onto a solid floor from an initial height h sub O. If the coefficient of restitution is 0.9, how high will the ball rebound? For bouncing objects, let's say this is our initial height h1. So after hitting the ground, it is expected to bounce not the same as h1, obviously. It is at a lower height. Let's say this is h sub 2. The coefficient of restitution for this case is the square root of the second height over the initial height. This is for bouncing object. So we have, what is our initial height? For this case, our initial height h sub 1 is equal to h sub O. We're looking for the equivalent of h sub 2, the rebound height. So coefficient of restitution, we have here that is given as 0.9. 0.90 equal to the square root of h sub 2 divided by our initial height h sub O. What will be the equivalent of h sub 2? That will be the same as 0.90 squared times h sub O. That is the same as 0.81 of the initial height. That will be our answer. 0.81, we have letter C.